have seen that what is adsorption isotherm. That means when we are talking about isotherm, it must be at constant temperature. So how there is change in absorption when we are changing the pressure under constant temperature, that is actually adsorption isotherm. So now we will see, if we take log both sides, then what will be the change in the nature of the graph, and also how we can find out the value of k and n in this equation. So the basic equation is that we have already seen in last class, x by m, that is equal to k into p to the power 1 by n. Okay, so here x by m and 1 by n, these these two values, they are actually constant. So how, by taking log both sides, we can get the value of k and n, that we will see today. So when we are taking log both sides, then it will be log x by m in the left hand side, and in the right hand side it is k into p to the power 1 by n. So when there is a multiple sign, it will be log k plus log p to the power 1 by n, and as it is power of pressure, it will be coming before log. Okay, so now this equation we can find similarity with y equal to c plus m into x. So here x is log p, so we will take it in the x-axis, and y is log x by m, it will be in the y-axis. Log k is the intercept c, and slope is 1 by n. So from slope and intercept we can find the value of k and n. These two are the constants. So here we have this graph, log x by m in the y-axis, log p in the x-axis. So the intercept is this length. So if we know the intercept value, we can easily find out log k. And slope, it is a positive slope curve. So if we draw this type of triangle, then this length divided by this horizontal length, that will give us directly the value of 1 by n. So if we know 1 by n, we can easily find out n. Now from this curve we can also prove whether Freundly's isotherm it is verified or not. So if after plotting log x by m in y-axis and log p in the x-axis, if we are getting a straight line, then it proves that Freundly's isotherm is verified, because according to this that is theoretical explanation says, as it is matching with y equal to c plus mx type of straight line equation, so it must be giving a straight line nature. But if it is not straight line, so it proves that from this isotherm it is not matching. Okay, it is not verified. So in this way we can find out the value of k and n. And one correction I want to make, in last class the value of n that I have mentioned here, see, this is mentioned that n is equal to 0.1 to 0.5. So it means as if 1 by n, that will be 1 by 0.1, 0.5, but actually it is not so. It is actually 1 by n is equal to 0.1 to 0.5. So this is the correction, that is, it will be 1 by n equal to 0.1 to 0.5. In this range only it will be matching with this portion. That is, if we look at this graph, it will be clear. That is the range between a and b, it will be such that where 1 by n is ranging from 0.1 to 0.5. But if it is greater than or less than this, for example, if 1 by n is 1, that means it is not falling in the range, then it will be k p to the power 1. So this is actually at low temperature, that is in this region, and here the line is perfectly straight line going through origin. And again when 1 by n is 0, that means again it is not in the range 0.1 to 0.5. In this case, this nature of the curve, it will be that such that the adsorption is not dependent on pressure. That is why now the line is parallel to x-axis. Okay, so this is the correction in last class. Next we will see adsorption in solution phase. So in adsorption in solution phase, you can see these two pictures. The first picture is solid gas system. So this type of system we have already seen. And the second picture is solid solution system. Okay. So what is the difference? In both cases we have solid surface, but here we have gas. This is also solid surface, but now we have liquid, that is solution. So solids can absorb solute from solution also. So it is possible from gaseous phase, that we have already seen. And now what we are seeing, the new thing, which is now it is absorbing solute from solution phase. So for example, suppose you have taken acetic acid in water, and you are shaking it by adding a charcoal piece. Now what will happen? As charcoal, it will act as adsorbent. A part of the acid will be absorbed on the surface of charcoal. So as a result, in the solution, that is solution phase, the concentration of acetic acid will decrease. So it proves that there must be some absorption process going on the surface of charcoal. Fine. Another example is, if we take litmus solution which is colored, and if we shake it with charcoal, after some time it will become colorless. That means litmus molecules, it will be adsorbed on the surface of charcoal. So these two are the examples of solid solution system adsorption, that is absorption in solution phase. Next we will see that in the case of absorption from solution phase, some observations are there. That is the extent of absorption, that is x by m, this value, it will decrease with an increase in temperature. Okay, so this type of observation we have already seen in case of physical adsorption. Fine. Increase with an increase in surface area. Now this has to be true, because when there is increase in surface area, more number of molecules of adsorbate can be absorbed. So that is why there is direct relationship with the increase in surface area of the adsorbate. It depends on the concentration of the solute in solution. Now as we are dealing with solution, so there is a particular concentration for the adsorbate particles, that is solute particles. So here the concentration of the solute particles, that also matters. Depends on the nature of the absorbent and absorbent. Now this is always true. That is, if that is solid system and the solution in which you are using some particular solute, that is actually adsorbate here, the solute is adsorbate here. So obviously these two, if changed, obviously the nature of that is the amount of absorption, extent of absorption, this x by m value, that will also change. And in this case, the equation that is followed, it has some similarity with the Fronley's adsorption isotherm that we have already seen in case of solid gas system. Only difference is, you can see, it is same type of equation. In previous case what we have seen, that is solid gas system, it is P to the power 1 by n. But now instead of P we have C, because it is solid solution system, so it must be concentration. So C is basically equilibrium concentration of the solute in solution. K is constant, N is also constant, and X and M, these are the mass of solute adsorbed and mass of the solid absorbent that we have already seen in case of Fronley's adsorption isotherm. So it is exactly same like this equation, only difference is now instead of P we have C. That is only difference. Otherwise it is just like the previous equation. Okay. Catalysis. So what is catalysis, and that we have to know, and after that we will see that there are two types of catalysis possible. So a catalyst will be defined as a substance which when added to some reaction mixture there is increase in rate of the reaction, but the catalyst itself, it will not be consumed in the reaction. That means it is not directly taking part in the reaction, but it is helping to increase the rate of the reaction. And how it is possible? Because when there is no catalyst we are using, the activation energy, this value is EA, and when you are using some catalyst, now the activation energy, it is decreased. Okay, So now the EA value, obviously it is lesser than EA, and you can see here we have only as if a single step reaction. But now when we are using catalyst, the nature of the curve is changing, and the highest point, because if you consider this point, this is not highest point, the highest point energy we have to consider if we want to get the activation energy with catalyst. So here from this nature of the curve, it is clear that the mechanism is changed when you are using catalyst and when you are not using catalyst, and energy, activation energy, as it is decreased, so obviously the reaction rate will increase. Okay, so this is the reason why when we use catalyst there is increase in rate. The reason is it is because of decrease in activation energy. Now it may be homogeneous or heterogeneous. So when we are talking about homogeneous, there is only one phase, okay, single liquid phase. So here catalyst and the reactants both are soluble, so that is why as if it is a single phase. So they are existing in same phase as the reaction mixture, and it may be liquid or it may be gas also. But if it is heterogeneous, now there will be at least two phases, so different phases will be there. So here we have liquid phase, this is liquid phase, and we are using the catalyst which is in solid phase. So you can easily understand that the two phases are easily visible. But if it is homogeneous, it is homogeneous, it is heterogeneous. Okay, so this is the difference between these two types of catalyst. Now we will see some examples. So this is the example of heterogeneous catalyst. So here we have some solid catalyst which is having some surface. The reactant molecules, this green particle and the blue particle, first it is adsorbed on the surface of catalyst. Some intermediate is formed, and after the intermediate formation, this is the adsorbed product. And finally there will be, that is, desorption process. So the product will be removed. So this is heterogeneous catalysis. And if it is homogeneous catalysis, obviously there will be no solid surface, because now it is homogeneous, so there will be only single phase. So that is why now the reactants, suppose there are total two reactants, and this is the catalyst, but all are in same phase. So unlike the previous picture, now we do not have any catalyst surface, and this is the intermediate formed, and finally catalyst is intact, there is no change, it is not consumed, but reactant is now converted to product. Okay, so mostly as this chapter is basically surface chemistry, so here we will be interested in heterogeneous catalysis mainly, because in homogeneous catalysis there is no surface of catalyst in. Okay, so our focus will be on the heterogeneous catalysis. We will see actual example, because the previous picture it is the general expression. Okay, so example of homogeneous catalyst: oxidation of iodide ion by H2OH2- ion, and here the catalyst that we are using is Fe3+. So the actual reaction is like this: I- is converted to iodine, and this H2OH2- ion is converted to sulfate ion. So how the catalyst is actually, that is, what is the role of Fe3+ here? So first, I- is not directly reacting with H2OH, it is reacting with Fe3+. So I- is oxidized to I2, and Fe3+, it is reduced to Fe2+. Okay, now the Fe2+ that is formed in this step, in the second step, this Fe2+ now reacting with another starting material, and again it is oxidized to Fe3+. So this is the original state of the catalyst with which we have started the reaction, and H2OH is converted to SO4. So this is the role of iron 3+ catalyst. Now if you just look at the first equation, you will not be able to understand what is the role of Fe3+. On the arrow, suppose simply it is written Fe3+. But if from these two steps, when it is written elaborately, now you can understand what is the role Fe3+ is playing here. In the medium it is converted to Fe2+, and again it is converted to its original state, which is 3+. So that's why we will say that the catalyst is intact. And both the reactants and catalyst are in the same liquid phase. So this is the example of homogeneous catalyst. Example of heterogeneous catalyst. Here obviously we will have some surface. So this is platinum surface, which will act as heterogeneous catalyst surface. And this is the gas phase where the reactant particles are there. So this is sulfur dioxide, this is oxygen. First of all, this SO2 molecule and O2, these are adsorbed on the platinum surface. Then reaction will take place, and finally there will be the product. Actually it will be attached with this surface, okay, and finally there will be desorption. So now the SO3 molecule is free. So here we have two phases. This is one phase, this is another phase, but that is not the case in case of homogeneous catalyst. Here the reactants in gaseous phase, and the catalyst, that is the solid phase. Fine. Now what are the steps that are followed in heterogeneous catalysis, that we will see now. First of all, the reactants diffuse to the surface of catalyst. So this we have already seen in case that is in the previous picture. First SO2 and O2 is adsorbed on the surface of platinum. So this is the first step. In this process, the reactants first get in contact with the external surface, out of which some of them get into interior through the cracks on the external surface. Okay, so some molecules, if there are some cracks, because the surface it is not necessary that it will be always smooth, so some will be entering into the interior through the cracks on the external surface. So suppose if the surface is like this, okay, so some cracks are there. So some molecules may be present here, some molecules may be also present here, but in both cases it is surface. This is also surface, and if you consider this portion, this is also surface. So it may be entering into the, that is inside the crack, or it may be in the outer surface. Both are possible. So these molecules, whether it is inside the crack or on the outer surface, in both cases it will be added to the suitable sites available for absorption. Now not all the sites are available for adsorption. There are some specific sites that are available for adsorption. So surface of catalyst, unlike the inner part of the bulk. So now we are talking about surface, we are not talking about bulk, okay. So what is the difference? When it is surface, there is some free valencies, and these free valencies provide the seeds for chemical forces of attraction. So these free valencies are actually the region where the adsorbed molecules, that is the reactant molecules, will be adsorbed. When a gas comes in contact with such a surface, what will happen? Its molecules will be held up because of some loose chemical combination. So there are some particular region, okay, that is suitable sites. Now the reactants, when bound to the surface, they will have higher probability of reacting with each, forming an intermediate compound. So now both the reactants are adsorbed, so they are close to each other. As they are close to each other, they can easily form the intermediate compound. So look at this picture. This is the catalyst surface where free valencies are available. These are the free valencies. This is the surface. Now the two starting material reacting molecules, they are adsorbed here. So now A and B, these two are close to each other. They can easily form this type of intermediate. And after the formation of intermediate, now the intermediate compound gets dissolved from the surface, giving availability for absorption for other molecules to come. That means now when the intermediate is removed in the form of product, the valencies are again free. So the next cycle can again start. So some more A and B will be adsorbed here, and in this way, that is in this cyclic method, the reaction will be going on. The intermediate compound disintegrates to form the final product, and which then diffuse out of the internal pores. So it will be diffused out to outside, that is in the outside phase. Suppose it may be gaseous phase or it may be liquid phase. So ultimately, as it is diffusing out of the internal pores, the external surface of the catalyst and also the internal pores, that is if there are some cracks, now both the surfaces will be again vacant and another cycle can start. So this is the mechanism, or we can say that the catalytic steps that are followed in the heterogeneous catalysis. Some important features of solid catalyst. So obviously, as we are saying solid catalyst, it will be heterogeneous catalyst. The first point is activity. So what is activity? So it is actually refers to the capacity of the catalyst to increase the speed of chemical reaction. Okay, so if the catalyst it is increasing the speed of the reaction when there is no catalyst, that is compared to the situation when there is no catalyst. If the speed is very high, we will say that activity is very high, but it may be that speed is increasing but not so much. In that case, activity is not very high. So this activity depends upon the extent of chemisorption. So if the chemisorption process is very good, then activity will also be increased. The adsorption should be reasonably strong, but see, it should not be so strong that the absorbed molecules become immobile, because that is not desired. We want the reactant molecules first it will be absorbed on the surface, then after reaction there should be desorption process. So the strength of this interaction, it should be some optimum nature, because if it is not this specific optimum nature, if it is very strong, then ultimately a reaction will be happening but product will not be dissolved from the surface, but that is not desired. So that is why it should not be so strong that adsorbed molecules become immobile. So as a result, there will be no vacant places for other reactants to get absorbed. So next cycle cannot start. Okay, so that is why here the adsorption, it should be some that is, it should have some optimum nature. The metals which lie close to the middle of the D block, they are the most active catalyst. Okay, so if we consider D block, just focus on the middle part, not the extreme left hand side and right hand side part, that is in the S block side and P block side. If we do not consider them, only the middle part, those metals are transition metals, they are very active catalyst. The second point is selectivity. Now this is very important, because and the important characteristic of catalyst. So selectivity, it means that ability to direct the reaction to form particular products excluding other. Okay, so it is selective for some reactions. There is some specific catalyst for some specific reaction, so they are very specific and selective in their action. Now a substance which acts as a catalyst in one reaction, it may fail in another reaction, because it is specific only for this reaction. So that is why it is specific. For example, if you look at these three equations, all are same starting material, carbon monoxide and hydrogen, but look at the products. In the first case, it is methane water, then methanol, and then formaldehyde. So what is the difference? You have changed the catalyst and products are also changed. In the first case, it is nickel, then copper, ZnOCrO3, and in the last case, it is simply only copper. So depending on what type of catalyst you are taking, though there are same reactants, but products will be different. Okay, so this is the specificity. Shape selective catalysis by zeolite. Okay, so what is shape selective catalysis? As you can see in the name, shape, that means the catalyst will have some particular shape, and depending on the shape there will be selectivity that we will be getting. So what is selectivity? That you have already seen in the previous slide, but if the selectivity is dependent on shape, that will be called as shape selective catalysis. Catalytic reaction that depends upon the pore structure of the catalyst. So there is pore, but what is the shape and structure of the pore? What is the size of the reactant and product? What is the size of pore? Okay, the radius of pore and the radius of reactant or product molecules. If that is, we are now talking about the shapes of the catalyst as well as the shapes of the reactant and product molecules. So these catalytic, this type of reactions, which is depending on the shape of catalyst as well as the starting materials, these processes will be called shape selective catalysis. Now under this topic, very good example is zeolite. So what is zeolite, that we have to know. So zeolites are basically shape selective catalyst because they have some honeycomb type of structure. So you can understand from this structure, there is a honeycomb type of structure, some pores are present. So all these are pores. So this is a three-dimensional structure. So they are microporous aluminosilicate. That is the chemical nature. If we want to know, it is aluminosilicate, having three-dimensional network of silicate. Now some, that is when we are talking about silicate, there is silicon atom. Now if some silicon atoms are replaced by aluminium, that is aluminosilicate. So zeolite is basically aluminosilicate. Now silicon, its oxidation, that is oxidation state will be +4 because it is from group 14, but aluminium, it will have it is from group 13, so its oxidation state will be +3. So when we are replacing silicon with aluminium, there will be one negative charge extra because now the positive charge is less. So here this is the silicate, this is Si, that is a small particle, and the large particle, this is oxide. Okay, now this solid black colored particle, this is aluminium 3+. So when one of the Si4+, so these are Si4+, but now you have replaced one Si4+ with Al3+. So basically now what will happen, there will be excess negative charge. Okay, so that is why it is written here excess negative charge, because one Si is replaced by aluminium and there is change in the oxidation state. As a result, there will be negative charge. So this is another structure of zeolite, and here depending on this pore size, it may be that some reactant molecules, they can pass through these pores, some reactant molecules may not pass through these pores. So depending on that, and it is not that only one type of zeolite is there, there are different types of zeolites. Okay, but the basic thing is that here, depending on the pore structure, depending on the shape of the pore, the selectivity will be different. Here zeolites, they act as shape selective catalyst either by transition state selectivity or excluding competing reactants based on their molecular size. So it means that the transition state selectivity, that is the intermediate that is formed, before the formation of intermediate there will be some transition state. So in the transition state, the starting materials, it may be 2 starting materials or 3 starting materials together, when it is making the transition state, there will be some particular size, that is volume of this transition state. Now if it is matching with the pore size, then this transition state will be allowed. So this is one possibility, that is the catalysis now it will take place depending on transition state selectivity. Another possibility is excluding competing reactants. Excluding competing reactant means suppose the pore size is such that only some particular reactant particle can pass through this. So that is that means there will be some competition between the reactants. Not all the reactants will be allowed in the pore structure. When some of the reactant molecules are too large to diffuse into the zeolite pores, it will be reactant shape selectivity. That means depending on the size of the reactant, shape of the reactant, some reactant can diffuse through these pores, some cannot. Contrarily, when only those products with the proper dimension can diffuse out of the zeolite pores. Now suppose reaction is over, reaction is complete. Now the product molecules, they must come out of the pores. But if it is not a proper dimension, it cannot come out of the pores. So then we will say it is product shape selectivity. So both these are the possibilities. It may be reactant shape selectivity or product shape selectivity. Certain reactions can also be prevented because the transition state reactants do not have enough space within the pores. So as it is mentioned in the first line, this is the actually saying the same thing. Okay, there exist about 40 naturally occurring zeolites, and some of them are, these are naturally occurring, but some are also man-made, artificial, that is synthetic zeolites, that is also designed depending on the requirement. And one of the most important zeolites that is used in petroleum industry is ZSM5. So what is its role? Its role is it dehydrates alcohol molecules. In alcohol there is carbon, hydrogen, oxygen. But if there is dehydration, that is removal of water, now it will be converted to mixture of hydrocarbon and directly gives gasoline. So gasoline is also mixture of some aliphatic and aromatic hydrocarbons. Basically this is hydrocarbons. Only carbon and hydrogen is present. So this is very important industrially, and here this catalyst is used, that is ZSM5, which converts alcohol into mixture of hydrocarbons. Okay. Enzyme catalysis. So this is another type of catalysis which is mainly known as biochemical catalyst, because enzymes are mainly used in vivo, okay, inside the body. Enzymes are actually complex organic molecules produced by plants and animals, so they are naturally produced. So these complex, they are very large in structure, complex organic molecules. They are actually protein molecules and mass is very high because they are very large in structure. They can form colloidal solution in water. Now they are very efficient catalyst under mild condition. So as these are biochemical catalysts and used inside the body in vivo, so obviously it should be mild condition, okay, because there is some particular pH or temperature that is maintained inside the for all the biochemical reactions. So it must be that is the catalysis must be under mild condition if we compare with other type of catalyst. Now it is because we have already seen that catalyst, why it increases the rate of the reaction? It increases because it decreases the activation energy. So more is the decrease in activation energy, higher will be the reaction rate. Now if you compare enzyme catalyst and some other type of catalyst, then the difference is here activation energies are much, that is reduction in activation energies, that is very high compared to other type of catalyst. So other type of catalyst, they also decrease the activation energy, but for enzyme it is very high, that is the reduction amount is very high. As we know that catalysts are selective, so obviously enzymes they are also selective in nature, different reactions, different enzymes. Now we know homogeneous and heterogeneous two types of catalysts possible. So if the enzymes are soluble, you can consider them homogeneous, but there are some membrane bound enzymes. So obviously now the question of surface arising, so that is why now it will be considered under heterogeneous catalyst. Okay, we have some examples here. Cane sugar and water, in presence of the enzyme invertase we are getting glucose and fructose. Okay, both are having same number of carbon hydrogen, but their structure is different. Next reaction is glucose in presence of zymase. Now it is converted to alcohol, that is ethanol and carbon dioxide. Starch, this is very large molecule in presence of n number of water molecules. Enzyme is diastase, we are getting maltose. And the fourth reaction is maltose in presence of water. Now it is converted to 2 molecules of glucose. The enzyme responsible is maltase. So sometime you will see that the enzyme, it has that is when we pronounce the name, it has some similarity with the name of the starting material. Several factors can affect the activity of enzyme and also for other catalysts, but here we are focusing on enzymes. So some factors are temperature, pH. We know that as it is biochemical catalyst and inside our body there is some particular pH is maintained for all the biochemical reaction, which is near to the neutral pH, that is 7. So it is pH dependent, and the concentration of the enzyme, that also matters, concentration of substrate and that of products. So these are the factors on which activity of enzymes dependent. Characteristic of enzyme catalysis. First point, highly specific in nature. Now this point we have already discussed, but why we are discussing it under enzyme catalysis again? Because there is some specific character which is involved in case of enzymes. So the catalytic property of enzymes, it is present at certain specific regions on their surfaces, and these particular regions are called active site. Remember, not all the regions are eligible for reactions. There are some particular portion where reaction will take place. There are a number of cavities present on the surface of the colloidal particles of enzymes, and these cavities, there is some characteristic shape present. And look at these groups: NH2, CO2H, SH, OH, that is thiol, alcohol group, amine, carboxylic acid. All these groups are present at the active site. Okay, so you can call them active groups. So the molecules of the substrate, that is starting material, they are actually having complementary shape so that they can fit perfectly into these cavities. So the cavity, there is a particular shape, and suppose there are different types of substrate. So among these different types of substrate, only that substrate is that is can undergo reaction which is having complementary shape compared to the shape of the active site. So enzymes are specific for a given reaction, so one enzyme cannot catalyze more than one. So if you look at this picture, it will be clear. Here the active site, the shape is like this. Now suppose there are different types of substrate, A, B, C and D. So see, A, the shape is oval type, this is square. Though these are very simplistic structure, in actual obviously it is not so simple, but just try to understand the concept. Substrate C, it is completely round shape, and here it is hexagon. Okay, so only a substrate C will be complementary in shape, so it can fit here. This is a C, but these three, they will not fit. Only SC, that is substrate C, will fit. So this is the specificity. Highly efficient, second point. So highly efficient means one molecule of enzyme, it may transform 1 million molecules of the reactant per minute. So see the ratio, just look at the ratio. One molecule of enzyme, and it can, that is 1 million molecules of substrate can undergo reaction. So 1 million times reaction will take place for one enzyme. So catalyst, as we know, after each reaction, once the reaction is complete, it will be remaining intact. So again it can start another cycle. So there are basically 1 million cycles possible per minute. So it is fast also. It is not that the number of reaction cycle is very high. Also the speed of this reaction is also very high. Per minute, this is the number 3. Temperature, optimum temperature. Rate of an enzyme reaction becomes maximum at a definite temperature, not below that temperature, not higher that temperature. Okay, so that is why we are calling it optimum. And also optimum pH. So at a particular pH, mostly it is ranging from 5 to 7 because it is biochemical catalyst, right? Inside the body there is restricted pH range. If the pH range is higher than that is lesser than 5 or higher than 7, it will be harmful for us. Okay, so that is why there is a particular pH range, and enzymes are also, that is their reactivity is maximum at this pH range. otherwise how they will react in vivo. Okay. Activators and coenzymes. So these are the two new terms. They have some relation with enzyme catalysis. So what is these two terms? Coenzymes, they are actually small non-protein molecule. This is actually vitamin. Okay, it enhances the activity of the enzyme. So enzyme is protein, but coenzyme, it is non-protein part of the enzyme, and it enhances the activity of the enzyme considerably. So this is about coenzyme. So if we look at this molecule, this is apoenzyme, which is protein because it is enzyme. Now if we look at this region, now when coenzyme is approaching, which is non-protein part, it will fit here. See, in this region it will fit here, and now the substrate, it is complementary to this coenzyme, so that is why now it can fit. But if the substrate without coenzyme directly approaching here, there will not be, it is no matching of shape. So that is the role of coenzyme. When it is inserted here, now it is complementary with the substrate structure. So now it is also called hollow enzyme. Okay, now it is active, but before coenzyme addition it is inactive. So this is the role of coenzyme. And what is activator? They are generally metal ions such as this. So these metal ions, when weakly bonded to enzyme molecules, they increases their catalytic activity. For example, in case of amylase, Na plus ion increases its catalytic activity. Okay. Inhibitors and poisons. Now from the name you can get the idea that obviously these species, they will disturb the catalytic activity. Inhibitor or poison, they interact with active functional group of the enzyme surface, and they reduce the catalytic activity completely or sometimes partially. So if we look at this enzyme, this is the active site. Now the substrate, it has complementary shape, so it can easily insert here, right? But suppose we do not want this reaction, we want to prevent this reaction, then if you add some inhibitor, now the inhibitor, it is also having the same shape. So if the inhibitor is inserted here, there is no active site vacant for substrate. Okay, so there is some competition, and inhibitor, if it wins over substrate, there will be no reaction. So example is use of many drugs that we take. Okay, it is related to their action as enzyme inhibitor in the body. So suppose inside the body some reactions we want to prevent that are harmful for our body, undesired reaction. So in that case, if we take drug, the mechanism of the drug will be such that it will act as inhibitor, it will block the active site, so the undesired reaction that will not take place. Okay, so this is the application. Mechanism of enzyme catalysis. So enzyme catalyzed reactions, there are mainly two steps. So first, enzyme plus substrate. This is the substrate complementary shape. Enzyme substrate complex. Once it is inserted here, now it is enzyme substrate complex. Now the catalysis is going on. Now it is changed to some other molecule. You can understand from the color change. So it is now enzyme product complex, not substrate complex. And finally product will be removed. So enzyme is free again. Another substrate can be inserted here. So it is now enzyme and product. So in step 1, there is binding of enzyme to substrate so that we get activated complex. So this is ES double dagger. Step 2 is decomposition of the activated complex to form the product. So now finally from ES double dagger we will be getting E and P. So this is E, this is P. Okay. So these are the two main steps in the mechanism of enzyme catalysis. Now a new thing we are starting, which is colloids. We have already seen solution in solution chapter, and suspension, which is another concept. In between solution and suspension there is another term, which is colloid. So what is the difference? If you are looking at the picture carefully, here particle size is gradually increasing. Okay, so in case of suspension it is maximum size. In case of suspension it is particle size is greater than 10 to the power minus 5 centimeter, and in case of solution it is lesser than 10 to the power minus 7 centimeter. So these two are the extreme, and in between these two extreme, if the range of particle size between, that is lesser than 10 to the power minus 7 but greater than 10 to the power minus 7. So this intermediate range, if the particle size falls under this range, we will call them colloid. Okay, so this is the difference with solution and suspension, the difference in particle size. But this that is, though the definition is very simple, that is only difference particle size, but so many properties are changed just because of this particle size change. Okay, so that is why there are three categories: solution, colloid, suspension, but we will focus on colloid. So between the two extremes of suspension and solution, there is a large group of systems that are known as colloids. So their particles, there is enormous surface area per unit mass, because now the size is small compared to suspension, so surface area will increase. So this enormous surface area, it leads to some specific properties for colloids. So these are exclusive for colloids. You will not observe these properties for solution or suspension. It is exclusive for colloids. Okay, and why colloids we are discussing it separately? Because they occur widely in nature, and as well as there is synthetic application, so manufactured synthetically also. So in nature you will see different kinds of colloids. So as its application and it is observed widely, so that is why it is discussed separately. Okay, its importance is very high. So here we have three, that is, this is solution. You can see this is completely transparent, right? And this is suspension. So this is exactly opaque, but in between these two, this is colloid, and in case of colloid, it is not completely transparent, it is not completely opaque, it has some translucent nature. Translucence means which is not exactly transparent, but it is not exactly opaque also, it is in between. So it is having translucent nature. So it is in between solution and suspension. So now we will compare true solution, colloids, suspension with respect to some properties. Visibility. As I have said, this is transparent, but here we are talking about the visibility of particles that are present in the solution. So it is not visible with any of the optical means. With naked eye, obviously you cannot see the particles. It seems as if simple transparent solution. Okay. So this is for true solution, but visibility for colloid, it is visible with powerful microscope only. So if you take normal microscope, you will not get it, but if you take ultra microscope, you will be able to see the particles. And in case of suspension, as the particle sizes are large compared to true solution and colloid, so you can visualize with naked eye. Transparency. It is transparent, this is translucent, that is intermediate of nature of transparent and opaque, and it is completely opaque. Sedimentation. True solution, no question of sedimentation, because it is completely transparent, you cannot see even particle. Okay, it settle down under high centrifugation. So if you just keep it for long time, it will not settle, but if you do centrifugation, then that is forcefully we can settle them down, but otherwise they will not settle. And in case of suspension, settles under gravity. So very good example of suspension. If you take sand particles in water, you just stir it and keep it for some time, sand particles, it will be settled down under gravity. Nature. It is homogeneous, but these two are obviously not homogeneous, which is clear from the fact that it is transparent, but these two are not so. Filtration. Now filtration, two types, with filter paper, with membrane. Now when what is the difference? In filter paper the pore size, and in the membrane the pore size, there is difference. In membrane pores are very small, but filter paper comparatively larger. True solution, you cannot filter them in by any of these. It is not possible because it is particle size is so small, it will pass through the pores whether you have taken filter paper or membrane. In case of colloid, with filter paper you cannot filter out, but with membrane you can do so. And in case of suspension, particle size are so large that with both filter paper and membrane you can do the filtration. And the last two terms, these are very important for colloids because this is completely exclusive for colloids. You will not see this effect, Tyndall effect and Brownian motion, in case of true solution and suspension. This is only special for colloids. Though in suspension it may be sometime possible, but as I am saying, it is mainly for colloids. And true solution, no question of Tyndall effect or Brownian motion. We will discuss them separately. That is, what is Tyndall effect, what is Brownian motion. Tyndall effect is basically optical property, okay, and Brownian motion, it is mechanical property. So in this way we can compare. So see here, it is not that all the points are different. Some points may be same. For example, if you see nature, both of them are heterogeneous. So that is why we are saying comparison, not difference. So some points may be same, some points may not be same. So here are the points that we have discussed: visibility, transparency, sedimentation, nature, filtration, and Tyndall effect, Brownian motion. Types of colloids based upon physical state of dispersed phase and dispersion medium. But before that we have to understand what is dispersed phase and what is dispersion medium. Colloids are heterogeneous system that we have seen already. So in this heterogeneous system there is one substance which is dispersed, and this is called dispersed phase, as they remain as very fine particles, and they remain in another substance which is acting as medium. So that is why it is called dispersion medium. So this is one phase, this is another phase, dispersion medium. So depending on dispersion phase and dispersion medium nature, that is if you do permutation combination of solid, liquid, gas. So when dispersed phase is solid, under this condition 3 possibilities are there. Similarly when it is liquid, under this condition again 3 possibilities, and when it is gas again 3 possibilities, but not the last one. Why? Because when you take dispersed phase gaseous, medium is also gaseous, there will be no that is different phase, because the gas molecules, they are completely miscible with each other. That is the property of gas. So as there is no heterogeneous, that is not two phase is present. If it is one phase, we cannot call it heterogeneous. So if it is not heterogeneous, it is not colloid. So that is why 9 possibilities are there, but 3 here, 3. But here it is not 3, it is only 2, because this is not possible. So that is why there is no example we are using, because all gases are miscible. So when both are solid, it is called solid sol. These are the examples. Solid, liquid. So medium is liquid but phase is solid. Example is sol, ink, blood. Solid in gas, aerosol. Liquid in solid. This is unusual, okay. This is gel, that is the name is gel, and example is jelly or curd. Liquid in liquid. This is also very common. It is known as emulsion, milk, cream. So these are natural examples, right? Liquid in gas, that is called liquid aerosol. For example, cloud, fog, again natural examples. Gas in solid, it is foam. Aerogel, pumice stone, and gas in liquid, it is foam. For example, shaving cream. So though there are total 3 plus 3 plus 2, that is 8 types of colloids possible, depending on what type of dispersed phase, dispersion medium you have taken, but some of them are very common. So out of these different types, The most common are sols, that is solid in liquid, and that is ink, blood. Then gels, liquid in solid, though compared to sols and emulsion these are less common. And emulsion, that is liquid in solids. Liquid in solid, liquid in liquid is emulsion. So these three are mainly very common. If the dispersion medium is water, suppose this medium is water when it is liquid, then the sol is also sometimes called aquasol, because this word aqua and hydro, these are derived from water, right? And if the dispersion medium is alcohol, it can also be called alkosol, and so on. So from the name you can understand what is the dispersion medium. Fine, aquasol, hydrosol, or alkosol. Fine. So these are the 8 possibilities, but among them 3 are mainly important, but mainly we will see salts and emulsion even more common than gels. Fine.